Hey everybody, happy Monday. Good to see you again, or not quite, but you can see me. Today we are going to go through 1.4, the composition of mixtures. So last week Thursday, if you remember, during live class we talked about 1.5, 1.3 rather, which was on pure substances, and we talked about empirical formulas and molecular formulas. So today we're going to talk about mixtures, which are going to be combinations of more than one pure substance. All right, so our objective, explain the quantitative relationship between the elemental composition by the mass and the composition of substances in a mixture. And it'll be a pretty quick, pretty simple day. Tomorrow you have a homework assignment due. That would be HW, or homework, Unit 1, Topic 1. So if you have not done that assignment, paper pencil, right? Because it is, again, it's in the back of your packet, right? So if you haven't filled that in or done that homework assignment, please do so, and then submit a picture if you could to It's Learning. If you're having issues with submitting the picture, or if you're not quite sure how to appropriately do that, or if you need instructions on how to do that, please reach out to me. I'm more than happy to help you kind of troubleshoot that and figure out how best to submit a picture for your homework. And then you can start working on homework topic 2. Homework topic 2 will be due, let's make it about Thursday by the end of the day. Okay, Thursday by the end of the day. I think that'd be a good time period for that one to get finished up. Topic 2 is kind of a mixture of some of the empirical molecular formula stuff mixed in with a lab scenario. I have a big lab scenario at the end of that homework topic 2 assignment, which is going to be a good thing because, again, we're kind of in a weird situation with difficulty being able to do labs. So anyway, let's get into 1.4. I'll talk more about topic 1 and topic 2 in the future, obviously in a couple other days. I'll have some more videos, obviously, throughout the week. We'll have a live class tomorrow, and I'll make sure that you have all the information you need to make sure you know how to accomplish all the things that I'm asking you to do. So, all right, so first things first, let's get the definition of a mixture. So a mixture is it's a combination of two or more pure substances. All right, so I've got some pure substance 1, some pure substance number 2. I mix them together, hey, and I have now made a mixture. Okay, that's all it is, pretty simple. Again, this is a common English word, so it's not just a chemistry word, right? You use the word mixture in all sorts of different contexts of normal life. So it's the exact same definition, right? You're mixing more than one thing with something else, right? So I have a picture of Gardettos down here, and Gardettos are substantially better than Chex Mix, and if you'd like to debate that with me, please feel free to jump in my office hours and, we can get real. Anyway, mixtures of chemical substances can contain any number of different pure substances. For example, if I were to take some salt, which is NaCl, sodium chloride, I mix that with water. Okay, salt dissolves in water, obviously, so we'd make some salt water. It's a mixture, right? I had one pure substance, NaCl. I have another pure substance, H2O. I put them together, and now I've got a mixture. All right. I could add more stuff to this if I wanted to. I just have some random examples, right? I could add some potassium bromide, some ammonium nitrate, some magnesium hydroxide. Doesn't really matter. I could add a whole bunch of different chemicals or different, substances, and it's a mixture, okay? I've got pure things combined together. It doesn't have to be two things. It can be any number, upwards of, hundreds of different chemicals or hundreds of different objects combined to make a mixture. So the reason why I got the Chex Mix down here, or sorry, I'm not even going to edit that out. That's just a horrible mistake. Gardettos, the reason why I have the Gardettos picture down here is because it's a mixture, right? You've got your pretzels, you've got your rye chips, you've got your whatever these little bread sticky things are, and they're different, but they're mixed together, right? All right. All right, so a lot of chemistry, a ton of chemistry, as a matter of fact. I should probably even emphasize that more. It involves either taking mixtures of chemicals and separating them, or taking pure substances and making mixtures. It's a huge part of chemistry. And we will go through a lab on Friday. Okay, I will have some sort of lab set up and lab recorded for you guys to kind of watch me as I work through some chemical stuff. And a lot of chemistry is one of these two things. Either I've got a mixture of things that I don't want combined anymore, So I'm going to determine a way or a method to separate them. Or vice versa. Hey, here's one substance, and I'd like to mix it with this substance and see what happens, right? Or we're going to make observations as we mix these two things together and determine the outcome. Now that's a chemical reaction, obviously, but you know, this is chemistry. You're taking things and either separating them or taking things and combining them. It's really one of those two processes more often than not. So another part of chemistry obviously involves being able to analyze whether you actually have a pure substance or a mixture of substances. So this does go back to last week with the mass spectrometer again. That instrument will analyze a chemical sample and let you know percentages of substances present, right? So if the percentages that you have from the readout of that instrument on your sample don't match mathematically with what you would expect if it was pure, well then there's something else there, right? There's an impurity there. There's a substance or a chemical in that mixture or in that sample that you don't want there. Maybe you need to purify it again or do another step in the process to try to separate what you have. So again, there are way more instruments than just the mass spec that we talked about last week. We are going to talk about a second instrument this week called a photoelectron spectroscopy or photoelectron spectrometer, whatever. Again, that spec word is kind of synonymous either which way you use it. But we're going to talk about more instruments, and oftentimes these instruments do something to help analyze what you got, right? I've been in the lab, I've been doing some reactions, I've been messing with this stuff, and now I want to know what I actually have. And that's where these instruments kind of come in and help us out. All right, so let's do a couple problems, and then we'll call it a day. I've only got 3 practice problems here. The first one, a student finds a container containing a white crystalline solid that is labeled KCl, which is potassium chloride. When the sample is analyzed, it's found that it contains 52.4% potassium and 47.6% chlorine. Is this a pure sample of potassium chloride? Explain. So, in order to answer this, we probably need to know what the actual percentages of potassium and chloride should be, right? If I have KCl and nothing but KCl in a sample, there's a specific ratio between those two elements in that compound. Now, when we give you these percentages, this is by mass, right? So 52.4% of the potassium means that I have 52.4% of the mass of that sample is from potassium, and 47.6% of that sample, or the mass of that sample, is from chlorine. So let's figure out what the actual percentages are here, right? So I have KCl. The mass of potassium, or the molar mass of potassium off of my periodic table, which again, you should always have nearby, obviously. I look up potassium and I find that it's 39.10. Okay, and that is grams per mole. And I look up chlorine and I find that it is 35.45 grams per mole. All right? So hypothetically, if I have a 1 mole sample, I would have 39.1 grams of potassium and 35.45 grams of chlorine. I should have those masses in a 1 mole sample of KCl. And we can determine the percentages that these should turn out to be, right? If I take the 39.10 and I add it with the 35.45, oops, that's not a 5. All right, I get 74.55. Okay, and that is grams per mole. That's the molar mass of my potassium chloride. Now the question is as well, what percent of that is potassium, what percent of that is chlorine? So we're going to do a percent calculation, right? I take my part. I'll start with potassium. The part is 39.10. Hold on, let me get the lights. There we go. 39.10 divided by the total, which is 74.55. And then I multiply that by 100 to get my percentage. Oops. And when I do that, 39.1 divided by 74.55, I'm getting 52.4% with 3 sig figs. Okay? And if I go up, that's exactly what this instrument or what the analysis was telling us, right? This sample was analyzed and it gave us 52.4% potassium present. Well, I just did the math and I also got 52.4% potassium for the pure potassium chloride. So they match. So here's the deal. I could do the math for chlorine as well, right? If I took 35.45 and I divided by that by 74.55, and I'll just do it, I guess, because I'm here, I get 47.6%. Well, if I go up, that's what's in the problem too, right? There's only 2 things present, so I don't really need to show the second part of this, because once I know the percentage of one of them, I can just take 100 minus that percentage to find the percentage of the other, all right? But long story short, some random white crystalline solid sample was analyzed, and it gave these percentages. Based off of the molar masses of these 2 elements in that sample, or in that in potassium chloride, the percentages match. So I would say that based on the math that we've done, okay, the percentages match. And then I would say this is a pure sample. Something like that. All right? It matches. We're good. All right, let's go to number 2. There we go. A sample that is supposed to be pure sodium acetate contains 15% sodium. Is this a pure sample? Explain. Kind of the same question, different chemical, different percentage, different element. So let's double check that, right? Let's go through and look at sodium acetate and figure out what the percentage of sodium should be in that sample. So I look up sodium on my periodic table, okay? And the molar mass of sodium is 22.99. All right? I need the rest of this because I do need the total molar mass, right? Because in order to get this percentage, I need to take the sodium part divided by the molar mass of the whole darn thing. So let's finish that. Let's solve for the total molar mass of everything. I'm going to format this one just a little bit differently. And if I have the total mass of the sodium acetate, okay, what is that molar mass? So I have 22.99 from my sodium. I have 2 carbons, which is going to be 2 times 12.10. Okay, I changed my mind. I'm going to show it all. 2 multiplied by 12.01. Did I say 10? I'm sorry, earlier. Grams per mole. That's going to equal something. I have 3 hydrogens. So that's going to be 3 multiplied by 1.008, because again, that is the different molar mass this year for hydrogen. And then I have 2 oxygens, so I have O equals 2 times 16.00 grams per mole. Okay? So let me punch all this in, right? I have 22.99 from the 1 sodium. This is going to give me 24.02. Okay? Grams. This is going to give me 3.024 grams, and this is going to give me 32.00 grams. I add all this up, right? So the 22.99 plus the 24.02 plus the 3.024 plus the 32. I'm getting a total molar mass of sodium acetate equal to 82.034. And again, I'm breaking sig fig rules here with my molar mass. That's okay. I want you to keep every digit for your molar masses, all right? So I am going to leave this with 5 sig figs, even though that looks like, well, it is not following the addition sig fig rules, okay? That's okay. All right, so I have the total mass of this compound. I have the mass of my sodium. Let's figure out the percentage. What should the percentage of sodium be in a sample of sodium acetate? And let's see if it matches the 15% that we were given. All right, so let me take my part. In this instance, my part is the sodium. So I have 22.99 divided by the total. which is 82.034. And I'm going to multiply that by 100, and I'm going to get a percentage. All right, so 22.99 divided by 82.034, and I'm getting 28.0%. Okay, so in theory, if I had a sample of sodium acetate and it was nothing but pure sodium acetate, nothing else present, pure substance, I would expect that I should have 28% sodium. Okay. But in this problem, it was saying that it was analyzed and it contains 15% sodium. So is this a pure sample of sodium acetate? It can't be, right? So, no, this is not a pure sample. Okay? And the reason is that the percentage of sodium in sodium acetate is 28%. What was analyzed was only 15. So it can't possibly be pure sodium acetate. The percentages don't match up. Okay? All right, last but not least, we have one more problem here that I'd like to run through. A chemist is attempting to separate a mixture of two salt compounds, sodium chloride and scandium fluoride. Sodium chloride will dissolve in water, scandium fluoride will not. Give me a step-by-step procedure to separate the mixture of these two into two pure solid substances. All right? Please pause the video. Try this. I want you to try this problem before I give you all the answers. Think about it, okay? I've given you a mixture of two things. Okay, these are both white powders, white crystalline substances. So they'd be mixed together. So you really couldn't tell which is which, right? It's just a kind of a white substance. So the question is okay, how can I get these two white powders, which are all mixed together, separate and have them as individual pure substances? Please pause it, try it, write your guesses down, give it a shot, and then I'll come back and obviously fix it. So pause the video, come back. All right, I hope you did what I asked you to do. And if you didn't, pause it, try it, please try it. It's gonna be a better mental process to try it than listen to me. Anyway, okay, I'm done. Let me go through it, all right? So step one. One dissolves and one doesn't. All right, let's dissolve the mixture, right? If I have two substances where one dissolves and one doesn't, let me try to dissolve it in water, because half of it will and half of it won't. So let's try to dissolve it in water. Now, the scandium fluoride won't dissolve. So it's going to be like a powdery, kind of cloudy junk that's just going to be sitting on top of the water or in the water, kind of suspended, but it's not going to actually dissolve in the water. So what should we do next? Well, we should probably filter out, okay, filter the scandium fluoride out of solution. Meaning, you would take that kind of watery, powdery mixture, right? Because again, the scandium fluoride doesn't dissolve, so it's just going to be kind of cloudy or suspended in that water. You'll take that and you'll pour it through a funnel with a filter paper. And I'll show that in Friday's lab, okay? We'll do it, I'll give you an example of this kind of process. And you'll pour it and the filter paper will catch all of that solid, okay? It'll catch all of the scandium fluoride that didn't dissolve. So that's step two. Step three, we will dry the filter paper containing the scandium fluoride. Okay? You can do this in an oven. An oven is an actual chemical lab piece of equipment. Now, obviously, at home you use an oven for, cookies and frozen pizza or whatever the heck. But in chemistry, you can use an oven as well. We need to dry samples sometimes. So that's what we'd do. We'd take the filter paper that we just poured that solution in, It's got the powder stuff, and it's all wet, obviously, and still from the water that it was suspended in. We take that, we put it in an oven, we dry it out, and now we have a dry sample of scandium fluoride. That's half the battle. I wanted two pure substances. I want the sodium chloride as well. Well, where's the sodium chloride? The sodium chloride is still dissolved in the water. So when I'm pouring that through the filter, the liquid that's falling through the filter paper is not just water, but it's also the NaCl, the sodium chloride that was dissolved in it. So now I need to take that liquid that I poured through the filter, okay. Oops. I'm going to say it differently, sorry. I'm going to say that I need to boil the I need to boil the water NaCl solution. If you take salt water and you boil it and you boil it and you boil it and you boil it and boil it and boil it until there is no water left, does the sodium chloride go with the water? Okay, have you ever thought about this? If you take salt water and put it on a stove, or on top of on a stove and boil it, right? Does when the water boils off or boils completely away, is the salt still there, or did the salt go with it? It's still there. Okay, the salt will not change phase. All right, the water will leave, the salt will be left behind. So this is what we want to do to get the NaCl powder back. So we boil this water until it's completely gone, and then we have nothing but NaCl left over. All right. So let me recap kind of a weird lab scenario that I'm giving you here. We have two substances. They're mixed together. They're both powders. They're both white crystalline powders, okay? And you can't tell the difference between them, and they're perfectly mixed up, so you can't tell which is which. I have sodium chloride and scandium fluoride. This dissolves, scandium fluoride doesn't. So first things first, I try to dissolve them. One of these will, one of these won't. What I'm left with is a solution of water with some suspended powder of scandium fluoride still in there. I need to filter that out. I filter it by pouring it through a funnel with filter paper. I collect the filter paper and I dry it. And what I'm left with after that is done drying is pure scandium fluoride. Okay? Because that didn't dissolve in my water. I then take that solution, the water solution that I poured through the filter and collected underneath, I take that and I boil it until all the water's gone, and there should be leftover powder or solid that kind of comes out of solution, and that's going to be pure sodium chloride. So after this is all said and done, I do have solid pure scandium fluoride and solid pure sodium chloride. Okay? All right, I'm all done for today. I'll give you more instructions later this week on your homework assignments and what we're up to on Friday and things like that. But until then, have a lovely day. Great to see you guys. We'll catch you tomorrow.